Now we want to find the maximum likelihood estimators of the coefficients in the chain ladder model. So in order to do that, let us first write up the analytical expressions of f and sigma as they are found in the example. In the example, we have that fj is given by 1 plus the expectation of the claim size belonging to development year j plus 1 multiplied by lambda j plus 1. And notation-wise, we denote this expectation using mu. We also have an analytical expression for the variance coefficients given by the second moment of a claim size belonging to the j plus first development year multiplied by lambda j plus 1. And we denote this second moment using the symbol kappa. Now, if you read the exercise, the example, then we are told that it is possible to to minimize the log, or should it be maximized in Jostein's case? It is possible to maximize the log likelihood function separately for the case of lambda and for the case of mu and kappa. So we can estimate lambda, j, and mu and kappa separately. And in fact, the example also gives us an estimate for lambda j already. So lambda j plus 1 is estimated using a ratio between the total number of observed claims when we stand in the j plus first development year, where we are asked to sum over all of the observed accident years. And then we divide by the total claims belonging to development year j summed over the observed accident years. So now that that part is done, what we need now is to estimate mu j and kappa j. Because if we have the estimates for mu j and kappa j, then we are actually done. Because then fj will be estimated as 1 plus mu j plus 1's estimate multiplied by lambda j plus 1's estimate, and sigma j squared can be estimated as the estimate of kappa j plus 1 multiplied by the estimate of lambda j plus 1. Okay, so let us just recall that since y, I, j plus 1 k is assumed to be log normally distributed with parameters gamma j plus 1 and tau squared j plus 1, then the nth moment is given as e to the n multiplied by the gamma parameter plus n squared multiplied by the second parameter divided by 2. So this means that mu j is analytically given by e to the gamma. Well, let's just write it with mu j plus 1 since that is the one we'll use on the top. It's given as e to the gamma j plus 1 plus tau j plus 1 squared halves. And we have that kappa j plus 1 is analytically given as e to the 2 gamma j plus 1 plus 2 tau j plus 1 squared and that's it, because 2 squared is 4 divided by 2. That gives a 2. So we have these two analytical expressions for mu and kappa, and we can see that if we want to estimate these two, then we need to estimate the parameters in the log normal distribution. So by invariance of maximum likelihood estimators, we see that the estimate for mu is just given as the analytical expression with the estimates for gamma and tau plugged in. And we also have the MLE for kappa in the same fashion. So all that our problem boils down to now is to find expressions for the estimates of gamma and tau. So find the maximum likelihood estimators for gamma j plus 1 and for tau j plus 1. Now, one thing that is useful to recall is that our claim sizes are log normally distributed. And if you have some random variable that is log normally distributed, then that means that log of that random variable is normally distributed with the same parameters. That means that log of yi j plus 1k is also normally distributed with parameters gamma and tau. So we can actually just estimate these parameters by considering the transformation, by considering the log transformation of the observed claim sizes. And due to the remark in the example about estimating lambda and mu and kappa separately, in the maximum likelihood estimation for these claim size parameters, we will also assume the realizations of the claim numbers are known. Okay. So since the log claim sizes are normally distributed, then we know that for the normal distribution, the mean value parameter is given by the average of the observations, and the variance parameter is estimated by, did I say given by here? I mean, the mean value parameter is estimated by the average of the observations, and the variance parameter is estimated by the average of the square errors. So we know from basic probability theory that the mean value parameter is estimated by the average of the observations. And how many observations do we have? Well, for a given development year j plus 1, we have nij plus 1 observations belonging to the ith accident year, and we have accident years ranging from 0 to I minus j minus 1. So this is given as the average of the total number of observations. And by observations, we mean observations log of yi j plus 1k. So this is given as the ratio, so this is given as C1 divided by the sum from I equal to 0 up until I minus j minus 1 of nij plus 1, because you have to divide with the number of observations when you take the average, and you sum all of these observations log of yi comma j plus 1 comma k, where you have one term for each accident year, and there are I minus j minus 1 accident years, and for each accident year there are nij plus 1 there are nij plus 1 claims. So you let k go from 0 up until nij plus 1. So here we have an estimate for the gamma parameter. And let us also just write up the MLE for the variance parameter in this normal distribution. So as I mentioned earlier, the MLE here is given as the average of the square errors where the square errors are estimated using the difference between the observed claim sizes taken log on minus, so the difference between these and the estimate of the average observation in this normal distribution, and we have to take these errors and square. And how many square errors are there? Well, there are as many square errors as there are observations, and we established earlier that there are 1 divided by the number of observations y for each accident year summed over accident years. Multiplied by the sum of square errors, and here we just use the exact same summation as we did above, but where we just sum the square errors instead of summing the observations themselves. And yeah, we now have MLEs for the parameters gamma and tau, which we can then plug in to the expressions for the MLEs of mu and kappa, which we can then plug into these expressions up here.